Good morning, fellas, boys and girls, Year 12 students. Welcome back to Princess Hill. What we're going to be doing today is we're going to be running a prac, and the prac is a chromatography prac. And specifically the one that we're going to be looking at today is this one here, the chromatography of vegetable extract. The vegetable that we're going to be using is silver beet. So that's the silver beet there. Very greeny leafy plants. We're going to extract some of the juices out of this plant, the chlorophyll and whatever other chemicals are in there. And what we're going to do is we're going to place it into a mortar and pestle, put some acetone in there, grind it up, get that juice coming out of the plant. The acetone will dissolve a lot of that stuff and put it into solution, and then we're going to transport that onto a plate, and this is called a thin layer chromatography plate. It's an very thin aluminium plate with a ceramic coating on it, and what happens is we put some drops along here. We'll go through that process in a second, and then we put it into a beaker containing a 1-to-1 mixture of cyclohexane and acetone. And what will happen is the chlorophyll and all the extract from the plant will start moving up this thin layer chromatography plate, and the transport mechanism is going to be the solvent. And the lighter chemicals or the lighter compounds will travel further, and the heavier ones, of course, will deposit a bit lower. We'll go through that in a second. So here we have our plant. We've put it into our mortar and pestle, and we're really grinding away here. And you can see there, we're starting to get a juice coming out of it. And voila, we've got our juice. So that's what it looks like. And it's a very greeny sort of suspension solution. Now what we need to do now is we need to put some drops of this onto our thin layer chromatography. But before we do that, we need to prepare our plates. So one of the key things is that we need to draw a line on this plate as our reference, and usually about 10 mils below the bottom, we'll just draw a line. This line has to be drawn with a pencil. Cannot use an ink base or a biro or anything like that, because then we'll have the inks in the biro or the inks transporting up, and we don't want that. So we use a carbon pencil, and it doesn't play a part in that reaction at all. And we've got to make sure that that line is above the solution that we're going to use. That's the solution, the 1-to-1 mixture of cyclohexane and the acetone. That's going to be our transport solution. That line has to be above it. So what we do now is we take our plate, and we have this thing called a capillary tube. It's just a hollow tube, and through capillary action draws up the chlorophyll and all that sort of stuff. And then what we do is we just gently put a dot on the plate. We're going to put 3 dots. We're going to do it 3 times. Now, because we're using acetone, it's going to dry real quick, so we just air dry it. It would be nice if these drops were smaller, but we can't get them any smaller than that. So we'll do it again 3 times. Give it a nice dry. And that's our 3 drops. So now we have our baseline. We're running 3 samples, and now we pop it into our solution. I'll get you that away for a second. So we put it into our solution, comes out of our solution, and 15 minutes later, like that, pull it out, and we have our 3 dots moving up the thin layer chromatography plate. Now, what we have here is the chlorophyll, and this looks like the carotene up here. If we kept going, we'll probably get another separation, but these plates are only that high, so we probably need to have a plate that's about another 40% longer. So this is basically thin layer chromatography using extract from the silver beet leaf. Now, this is one technique of chromatography. Another technique, this is wet chemistry chromatography. We just happen to have at the school a GC, which is gas chromatography equipment, and I'll quickly come over here, just for the sake of introducing you to it. This is a GC, gas chromatography, and essentially it's the same thing. We have a port here where we put our chemical, and it's automated, feeds into the system. It's got a radioactive source, and what happens is here, that gets pumped through the system, gets heated into in a thin, long stainless steel tube. You can see it in there, and then what happens is the lighter compounds move further, and the heavier ones don't travel as fast. And using the radioactive source, we can determine what they are. It's all computer driven, very complex to use, way beyond most of people's expertise. This is sort of university stuff. But that's basically it. So there you have your chromatography plate, and your teacher, Annette or Al, will go through with you on all the ratios and distances and all that sort of stuff. Enjoy. See you in the next one. Great. Good morning. Once again, welcome here to the Princess Hill 3 out of 6 lab. What we're going to do today with the Year 12 students for you is we're going to do what's called a preparation of a standard solution. We're going to run a demo. Normally you will be doing this yourself, but we're going to go through the whole process, and in particular today we're going to make a standard solution of sodium carbonate. It's going to be roughly a 0.1 molar solution. Yeah, 0.1 molar solution. And typically you would titrate this, use this in the titration. We need to know the exact amount or the exact concentration of this solution that we make, because it is a standard solution. A standard solution is a very, very, very accurate solution that we know the concentration of. And that's usually limited by your scales. And in this particular lab, we can measure here to 10,000ths of a gram. So that's 1 gram, 0.1, 0.01, 0.001. So, and there's always an error associated with this, and it's usually half the smaller scale division. So this is the smaller scale division, which is 10,000ths of a gram, plus or minus 5 10,000ths of a gram. Your teacher will work the errors out for you if she wishes to go down that track. But for our purposes today, we're going to prepare a 0.1 molar standard solution of sodium carbonate. So now the first order of business is to determine how much quantity we need. Now it doesn't have to be exactly 0.01, but we need to know the exact concentration, and the way we do it is as follows. So Na2CO carbonate, and what we do is, the formula is number of moles equals the mass over the molecular weight. So we want 0.1 mole of substance multiplied by the molecular weight gives us the mass that we need, and then we put that into solution, and it becomes molarity, and we're going to do it at 250 mils, which means that we divide it by a factor of 4, because normally molarity is worked out per litre, so we're going to do it in 250 mil, because we're going to use a 250 mil volumetric flask. Now this is a very accurate flask at 25 degrees Celsius. There's a line there, I don't know if you can see the line. The meniscus has to be at the bottom of that. Once we put our chemical in there, fill up with distilled water, we know that there's 0.1 molar at 250 mil volume exactly. So one of the most important things is we need to use an analytical grade chemical to start with, and this is the sodium hydrogen carbonate. sodium carbonate, not sodium hydrogen carbonate, rephrase that. And this is anhydrous, so it contains no water in it at all. And this is the array or the assay of what's in there, so the percentage of impurities. This is analytical grade, so it's fairly clean. And down here, Na2CO3 has a molecular weight of 105.99. So we'll write that down. So the molecular weight of Na2CO3 is 105.99. So if we come over here and we plug it into our formula, 0.1 multiplied by 105.99 is the mass required in 1 litre. So 0.01 times that is 10.599 grams in 1 litre. We only need 250 mils, so it's divided by 4. So 10.599 divided by 4 is 2.645, we round it up, grams, in 250 mils. Now if you look over here, somewhere here they've done the calculations for you, very close, 2.65, so that's how we came to that figure. Now let's go ahead. Now we need to weigh out about 2.64. It doesn't have to be exactly 2.6459, whatever. What we need to do is weigh out an accurate amount. So here we have our analytical scales, we zero them, and we'll get our clean watch glass and we'll put it in there, zero that, now we get our analytical grade. Now most of you, when you do this experiment, we don't give you the commercial container, we give it to you in the smaller containers, guaranteed it's the same stuff. So let's weigh this out. We need about 2 grams. .6 grams we need, so let's weigh it out. That's way over. So let me take some out. It's still too heavy. Okay, what we've got here is our weight is 2.783 grams. Okay, so going backwards, this is going to be a little bit more than 0.1 molar. It's going to be greater than 0.1 because we're using a fraction more. Your teacher will go through and explain to you how to go backwards and work out your actual molarity of this standard solution. Now, once we have our standard solution in our boat, now this container here is a watch glass, but it becomes our boat. This substance here is quantitative, so it's an exact amount, and now we need to transport this into our volumetric flask here. And the way we do that is put the funnel on there, just tap it gently. Now, because this is so accurate, we've got residual stuff on our watch glass. Okay, we need to wash all that down. So all that's gone down, all right, nice and clean. Then we need to wash that down. Okay, then we need to wash that down. Wow. So now all of our chemical is contained in there. Now we need to bring the volume of the distilled water up to the marker there, which is the volumetric mark of 250 ml. And take the squirt bottle off and we'll just bring it up pretty quickly in the beginning. Now you need to get it up there. One of the good practices is to get it up to about there and then swirl it. Because once you start filling it up, it's very hard to dissolve all that substance in there. Well, for our thing today, now that'll take a little while to dissolve, so let's, for the purposes of preparation of this standard solution, we'll bring it up to the mark. Okay, just let it sit there for a while, get all those bubbles out. Persistent bubbles there. Gone. Oop, not quite. Okay, that's not too bad. There we go. Now what we need to do now is come down to eye level and gently bring that right up and not to go over the limit. The bottom of the meniscus has to be in line with the... Now all these air bubbles in here are taking up space, so what will happen is if you let this rest, that level there will drop a fraction and then you come back and top it up to the line. But that is how you prepare a standard solution. You can go one step further and titrate this against another standard solution. You can work out all your errors and all that sort of stuff. But for the purpose of us today, that is pretty much how you prepare a standard solution. You can see those bubbles there. They're still coming up and the level's actually dropping. There's a lot of air bubbles in there still. Okay, there you have it. That's how you prepare a standard solution, fellas. Enjoy. We'll see you in the next video.